you can then also multiply that with field band and then transform flat indices in curve indices and vice versa. You can lower or raise indices with the field band as usual. But that's kind of the basic definition, which traditionally it's written in this way. As I said, you can write actually also the Riemann tensor, namely what's called as curvature 2 form, which is a slight variation on the view of the Riemann tensor. Let me just write it and explain it. So it's an object which has two flat indices and two space-time indices, and that's given in terms of the spin connection. This is called curvature 2 form, and so it is antisymmetric in these indices. That's why it's called the 2 form. And for example, you can write various quantities which were expressed here in terms of this, the original Riemann tensor and its contraction here, the Ricci tensor, and so on. You can re-express in terms of this curvature 2 form and contracting the flat indices with the field band. For example, the Ricci scalar can be written as this contraction here. You take to field band and sorry, and you contract this in this way. Right. So the reason why I mentioned this is it's useful when we want to write things in terms of the field band, as I'll do in a few seconds. Okay, so we are now ready to start talking about supergravity, and this is done by introducing an action known as Rarita-Schwinger action. Okay, that's nicely actually on the same side as the Einstein-Hilbert action, which takes the following form. So we keep the same overall factor, and then we write, and here is where I should start specifying what are the gamma matrices and so on. So as I said, if you want, you can keep d equal 4 in the next formula, but I will write with general d. There is absolutely no problem in the bosonic that part concerning the metric in keeping general d. So here I start writing the determinant in this way, and then I write the following Lorentz invariant contraction, where I will explain all the ingredients subsequently. Okay, so psi mu is the Rarita-Schwinger field, which is known as gravitino. And it is an object which has both a Lorentz index and a spinorial index, which is hidden in the notation as usual. So there is a spinorial index which could be made explicit by writing some alpha or something, but I will not write it. And that's the index where the gamma matrices act. This expression here stands for an an anti-symmetrization of gamma matrices. So let me just write it. So this, by definition, is gamma mu, gamma nu, gamma rho, and then totally anti-symmetrized on the indices mu, nu, rho. There is also another anti-symmetrization of gamma matrices which enter into this capital D, which defines the covariant derivative acting on the Rita-Schwinger field, which involves the spin connection itself, and then is gamma AB, where gamma AB is the generator of Lorentz transformations. So it is simply the commutator of gamma A and gamma B with a factor 1/2. Okay, so these are all the ingredients that one needs in order to write this this action. Here the bar is the usual bar, and then we have all the ingredients to discuss supersymmetry in the context of supergravity. So this is the claim. The claim is that if I write a total action, which is the Einstein-Hilbert action plus the Rita-Schwinger action, then this is invariant under a local, and that's the key, supersymmetry transformation. So any supersymmetry transformation involves some parameter, and the fact that it's local means that this parameter, typically called epsilon or some other similar letter, becomes space-time dependent. So that's why it is a local transformation. I'm sure in the context of quantum field theory you've seen this distinction between global and local transformations, and the same applies in the context of supersymmetry. So what you normally take as a global spin-Euler parameter becomes, in this case, a local spin-Euler parameter. And the transformation itself, for which epsilon is the parameter, has to be done on the two fields which we have defined and which enter these actions, namely the metric G mu nu and the Rita-Schwinger gravitino field. Since we're using the formalism which uses the field bind instead of the metric, then we give the supersymmetry transformation of the field bind. And the supersymmetry transformation of the gravitino is given by this, where the covariant derivative is the same that appears there. So let me write it. Okay. So the claim, and I will try to sketch the proof of this claim, because I think it's quite instructive. The claim is that delta of this S total is equal to 0. So if you do these supersymmetry transformations and you plug them in, then you find that the total variation is 0. I could leave that as an exercise, or I could try to embark in a sketch of a proof, which that's what I'll do, so that you can maybe feel the details later on. So we have to compute, it's quite straightforward in principle, although there are some technical manipulations, especially in the variation of this action that one has to take care of. But the Einstein-Hilbert part is slightly easier, so let's start from that. So we start writing the Einstein-Hilbert action in terms of the Ricci scalar expressed in terms of the Riemann curvature. This is factor of 2. So E A mu, E B nu, R mu nu A B, right? And then we have to take various variations. So you have to vary E, you have to vary the field bind, and you have to vary the Riemann tensor itself, and just applying the usual Leibniz rule. So I will leave some of these details for you to check, but let me just sketch it. So from the variation of the field bind here, you have to be careful because here the field bind is defined with two upper indices. So here I gave the variation with the lower index, and in gravity or in supergravity in particular, you don't lower and raise indices carelessly without checking what you're doing. So you have to check what you're doing with that, and you find that if you check it carefully, you find that there is a minus sign when you vary the field bind with one index up. So you get this gamma psi B, let's say. Let's say A, and then E B nu. There's also a factor of 2 because there you have two terms here. Then you have to vary the field bind, sorry, the determinant of the field bind. And again, it's a simple exercise to check that the variation of the determinant of the field bind is proportional to the determinant itself. And then it involves this traced version of the variation. Good. And okay, you have to multiply this with R mu nu AB. And then you have to vary the Riemann tensor, but actually it's a relatively standard exercise to find out that when you vary the Riemann tensor, and here you are using the expression which I wrote earlier in terms of the spin connection, that's a total derivative. So inside the action, it doesn't contribute. So you get plus 0 from here. So when you rearrange all the terms, here you get something nice looking. You get up to the 2k square, the x, and here the so-called Einstein tensor is reconstructed. Multiplied by this object here with two indices. Okay, so that's the variation of the Einstein-Hilbert action. And then we have to do a similar exercise on the variation of the Rita-Schwinger action. So let's do it here. So here, if you really wanted to do it very carefully, it would be very hard. Yeah? Yes, I missed some indices. So I compactified too quickly the expressions. So let's write it in this way. Mu nu a b, and I think if I put an r here, it should be fine. The index on the first gamma is a mu. Yeah. Well, I'll see. Yeah. Yeah. Okay. Right. So let's put this rule. If you know already the answer to your question, don't ask the question. Right, so let's go back to the variation of the Rorita-Schwinger action. And as I was saying, this is a bit more complicated, I mean, quite more complicated if you really follow through the definition of the variations over there, because you get quite high order terms in the fermions. But the common approach, which has been used also historically, is to study a version of the variations where you just focus on the linear terms in the fermions, and then worry about make it complete later on, right? So this is exactly what we'll do, as most of the people normally do. But we have to know when this completion is possible and when it's not. So I'll mention that later. Right, so we have the supersymmetry variation of the Rorita-Schwinger field and action. We have to use things like this, for example. Right. So at first order in the variation of the fermions, you can pass through the variation inside the covariant derivative, but you would in principle, you have higher order terms that we are neglecting. And then, if you do that, soon enough, you'll find this expression here. So, okay, there's a 2k square again. There's a factor of 1/2, and then the following thing appears. Okay, so let's follow through the index structure. Here you have these antisymmetrized gammas. This has also spinorial indices, and then you have to multiply them through this gamma AB, which has also spinorial indices, and everything is sandwiched between the epsilon parameter and the bar of the Gravitino field. And then this Riemann tensor, or Riemann curvature 2 form appears, and the way this one appears is through some appearance of some antisymmetrized, okay, keeping the same notation, gamma d nu d rho, right? And this is a quite standard exercise to compute this anti-commutator. Sorry, I keep saying anti-commutator, commutator of derivatives. And you find, it's called fundamental identity or something like that, and you get out the Riemann tensor. Anyway, so getting to the bottom line, of course, you would not be surprised that when you manipulate these products of gammas, so here you have 3 gammas, you have to multiply by 2 gammas, and then again expand this by using properties of the gamma matrices. With enough time and patience, you will find out that the expression that you get is exactly minus this, right? So that's where we are going. Yeah. Yes. Just put whatever your preferred indices are and multiply them by the field bind or the inverse field bind. Right? So if you want these to be all curve indices, you write this simply as gamma A B E A mu E B nu. Yeah. The algebra is just the algebra obeyed by the space, not space-time dependent gammas, and then you make them space-time dependent by multiplying them through field bind. Right. So, for example, if you want to compute in Mathematica, you would use the flat space indices, where the gammas are not functions, but they're just constant matrices. All right, so the bottom line is that if you believe a little bit of the details which I sketched, it's not too difficult to show that the combined action of the Einstein-Hilbert and Rita-Schwinger term is supersymmetric. So namely, it's invariant under these supersymmetry transformations if we keep the check up to linear order in the fermions, neglecting the higher order terms. However, if you really want an action to be fully supersymmetric, not just approximately supersymmetric, then you need to know whether it's possible to make it completely supersymmetric. And the answer to this question turns out to depend on the number of dimensions and also the details of which representation you are using, which kind of conditions you are imposing on your fermionic fields, and so on. So in 4 dimensions, which is the kind of the safe territory, it's known, so I can claim that one can write a completion to this computation, basically. So what you have to write, you don't modify, well, essentially you have to modify the action by adding extra terms, which are cubic in the fermions, and that will compensate. And the claim is that this is possible. It's not very easy. This has been done in the past when our forefathers had constructed the supergravity theories. But it is not always possible, and in some cases you need to introduce additional fields. So this is one way in which you will see the necessity of introducing more fields. So you can't have supergravity and live happily ever after with the metric and the gravitino. But in some cases, if you want a gravitational theory, which is also supersymmetric locally, then you are forced to introduce more fields. And the fields are typically both, in principle, bosonic fields and fermionic fields. In some cases, like in 11 dimensions, which I will discuss perhaps on Thursday, then you can actually just achieve this program by adding a bosonic field, and you still have only one gravitino and no other fermionic fields. We'll see that later on. Okay? So, but in 4 dimensions, we don't have to add additional fields. All right. Sorry, what epsilon prime?
Variation of action of RS.
Mm-hmm.
There's a parameter epsilon.
Yeah.
The other one is parameter epsilon bar, the Einstein.
So epsilon bar is like the dagger of epsilon, essentially, up to some possible gamma 0 that you have in Lorentzian signature.
But we want to cancel each other to show that they are the total action is in.
Yeah. So you can have things like, for example, psi bar mu something epsilon, right? And in general, this is a complex number in general. But here we are imposing, as I said, secretly some Majorana conditions. So this is a real thing, right? So since it's a real thing, then you can take the star of everything, which is the same as the dagger of everything, which means that this is equal to epsilon bar something dagger psi mu. Okay. Otherwise, in general, you have to worry about this complex issue. But here, to simplify slightly the computations, I'm assuming that there is a Majorana condition. That's why I'm not completely sure how the computation modifies, say, if you are in 7 dimensions. I've not really checked, but it's possible to do that. The important point is that the full nonlinear completion of this action is possible only in 4 dimensions, right? That's the message, the takeaway message. Now let us study some consequences of this supersymmetric action. The first one, and the most trivial but useful, are the equations of motion. Okay, so the equations of motion, the Euler-Lagrange equations, this action. Let us write them. Okay, so that's the equation for the graviton, the metric, and this is the equation of motion for the Rorita-Schwinger field. This T mu nu of psi mu is the energy momentum tensor that you compute from the action. Standard exercise, it doesn't matter, but this is kind of what gives what is called matter in the Einstein equations. Now, in many situations, we will be interested in solutions, so solutions that solve the equations of motion here, or the generalizations which I will discuss, where the fermions are set to 0. Right? So the physical reason for that is that we are interested in some background spaces, which that we will use then to construct our quantum theory on top of it. And then in this kind of ground state, the fermionic fields have to vanish. So in particular, if you have only the gravitino, then psi mu is equal to 0. And then I can take a colored chalk and cross out this term. Right? So in this case, this is equal to 0, which standard computation tells us that this is equivalent to the Ricci-flat condition by taking the trace of the Einstein tensor, and this is solved trivially, right? So if psi is 0, this is solved. So spaces which obey this condition are called Ricci-flat. They are interesting, despite their appearance to be trivial, and quite rich, in particular in Euclidean setting. And the reason why they're interesting is because they are related also to the notion of supersymmetric solutions. So in what sense? Now, since psi mu is equal to 0, if we want to preserve some fraction of supersymmetry in a background, then we have to impose that the variation of the fields are equal to 0. So this we get for free, because that's the variation of the field band, which is proportional to psi. That's equal to 0. But from the variation of the gravitino, we get a non-trivial equation, which looks like this. So let me actually box this, because I will come back to this more and more time, and I will always be able to write something of this form schematically, but every time I will have to tell you what exactly do I mean by d mu, and in this d mu will be hidden a lot of structure, which I will explain. In this context, d mu is simply the d mu that we defined earlier, so it's the simplest covariant derivative acting on epsilon. So let's write it. It's d mu epsilon plus 1/4 omega mu AB gamma AB epsilon. So this equation here is actually, so it's a non-trivial equation for the coupled system for G mu, because G mu enters into this in the spin connection, and for epsilon itself. Right? So spinorial parameters which obey this condition are called killing spinors. And the equation itself, it's referred to as killing spinor equation. So if in our background, which is by definition a configuration of bosonic and fermionic fields which solve the equation of motion, the supersymmetry variations are also equal to 0. These are called supersymmetric solutions. And equivalently, there are solutions for which there exists killing spinors. So there must be at least one solution. You can have more than one independent solutions, then you would have a more amount of unbroken supersymmetry. So let me illustrate this to begin with a trivial example, and then as we go on, we will find less trivial examples. Actually, I like to be interactive in my lectures at the university, so I will keep the same tradition, and I will ask if anyone would suggest a solution for this equation here. Sorry? Yeah, and what is the metric? Yeah, that's right. So the simplest solution is just Minkowski space. So epsilon constant, constant meaning the appropriate number of spinorial parameters, which are all constant, right? So here this is 0. And in addition, if you pick the Minkowski space, the spin connection is also identically 0, right? Because the curvature is 0. So you take G mu nu to be eta mu nu, and that's a supersymmetric solution of supergravity. Here we go. We will be interested in less trivial examples. So, as I mentioned, let me actually write it somewhere. At least in Euclidean signature, solutions that solve this equation here, and also this equation here, they're called special holonomy manifolds. Okay, so this would take us in a direction which would be nice, but it's not the appropriate place to continue on that. Those of you who have heard about special holonomy manifolds or Calabi-Yau manifolds will be happily recognize that those solve this equation here. And for me, this suffices to introduce a slogan that I would like you to have in your mind, which is that supergravity and supersymmetry, namely imposing supersymmetry conditions, they are related to geometry in a very nice way, in a very rich way. Actually, this has a role even in the ADS-CFT correspondence, but before finding out about this role, there is still some work to be done. And the next thing I would like to do is to introduce a slight generalization of the supersymmetric supergravity theory which I wrote, which will allow me to also write a modification of this supersymmetry equation, so a slightly modified killing spinor equation. And that immediately will lead us to anti-de Sitter, right? So we will be ready to go. So I'm not talking about these facts just because I like them, but also because they are relevant for the ADS-CFT correspondence. So the modification that we want to introduce, it's very slight, and it's that of adding a cosmological constant. If we were just at the time of Einstein, we should not worry too much. We take the Einstein-Hilbert action and add a constant term, and that's it. But since we want to preserve supersymmetry, we want to worry about whether it's possible, and if it's possible, how to do that, introducing a cosmological constant in the bosonic part of the action and modifying the fermionic part in such a way that the full thing is still supersymmetric. It is possible, of course, and let me give you the answer. So in keeping with my notation of the generic, we have the old terms, the Einstein-Hilbert plus the Rorita-Schwinger. And we have two modifications. We have the cosmological constant that has to pick a particular, well, in some particular conventions, has some particular value. And this value depends on the number of dimensions. And there is also a fermionic modification to the action. Sorry, I don't want to go on the next line, so let me write this in a way that you can't read it. Okay, so these are the two modifications to the initial supersymmetric action that I have to introduce. So if I want to introduce the cosmological constant, I have also to modify the action with another term for the fermionic, for the gravitino field. And this is the action, and then I can now discuss in turn the supersymmetry variations, how they're modified, and the consequences of that. So let's write it. Actually, the supersymmetry variations over the field plane is unchanged, so I will not copy that. And the supersymmetry variation of the gravitino is changed in a small way. And as I promised, I can hide, if I want, this change into the definition of a new operator with d mu with a hat. Right? So it looks like that, apart from the hat. And the hat is hiding the fact that this is equal to the old, the covariant derivative, plus a shift, which is proportional. It's related to this cosmological constant. So there is a constant called L. So I will try to keep this constant L throughout the lectures, always the same name. And I will also give the physical meaning of this constant in a few minutes. Okay, so the modification involves a shift by just a single gamma. So for those of you which are already thinking ahead, you will recognize that this term can never be written in terms of a Lorentz generator, right? Because there's only one gamma, so it cannot be reabsorbed into the spin connection. So it's a genuine modification of the covariant derivative here and of the variation here. The equations of motion, namely the Einstein equation and the Rorita-Schwinger equation, are also modified accordingly from the action. For example, the Einstein equation reads r mu nu minus half r g mu nu is equal to 1 over 2 L squared d minus 1 d minus 2 g mu nu. And from now on, I will not write any more equations of motion that involves fermionic fields, right? So from now on, I will take the logic that you are interested in studying backgrounds of supergravity, and in the backgrounds, we will always have psi mu or other fermionic fields equal to 0. So the reason why there is no fermionic field into this equation is that because I put them to 0. Otherwise, there would be a contribution to the energy momentum tensor, which involves the gravitinum. In any case, that's the bosonic part of the modification of the Einstein equation. And by definition, up to a factor here, this is called cosmological constant, right? So this is called lambda. You can take, for example, from here, you can take the trace of this equation, and then you can slightly simplify that. So this equation here, it's equivalent to this equation here. Again, nice, simple exercise. I encourage you to do that. Trivial exercise. Show that these two equations are equivalent. In this form, it's more evident that the Ricci tensor is proportional to the metric itself, and by definition, a definition which is also used in the mathematics community, these are called Einstein spaces. So the Ricci flat case is a special case in which the cosmological constant goes to 0, or you can take this formally as L going to infinity of an Einstein space. Otherwise, this is a finite number. Now, if you take a further trace of that, and you find that the Ricci scalar is equal to the following definite number, which is always negative. Okay, so in some conventions that, of course, had to be declared from the beginning about the sign of the Riemann tensor, but in some quite universal conventions, we say that these spaces here have negative curvature. So if your preferred example of space with positive curvature is a sphere, in this convention, the sphere would have plus something, would be the Ricci scalar of the sphere would be plus some number. And in that convention, the Ricci scalar of the Einstein space that arise as solution of the supergravity equations is a negatively curved Einstein space. And that sets the stage for me to talk about ADS, which I will do after the break, okay? If you want to take advantage of it, about 5 minutes. Yes, no more than 5 minutes. So a remark which I think I forgot to make before the break is that the Killing spinor equation now takes this form here, right? So the variation of the gravitino field now takes this form, where on the right-hand side of the ordinary covariant derivative, which contains only the spin connection, there is a term with 1 gamma. And in fact, it's also a relatively simple exercise to show that this condition here actually implies that this condition. So supersymmetric solutions imply that the metric is an Einstein metric, but not the vice versa. So we'll not write a double arrow because that's not true. So this is a stronger condition than that. And often this is called integrability condition, which means that it's a necessary condition that the metric has to satisfy in order for it to be possible that there exists solution to this equation here. Okay, so we have introduced a more general action with the more general equation of motion, and also a slightly more general Killing spinor equation. So de Sitter, right? One of the two main characters of the ADS CFT correspondence. Right? One can say many things about de Sitter. I'll try to introduce this from the angle that I decided to take. And the angle is that this is, so I will abbreviate ADS. With subscript D means in D dimensions. So D is the total number of dimensions, so there will be D minus 1 spatial and 1 temporal. So we can say that ADS D is a solution to, let's put some names here. Let's say 1 and let's say 2, okay? So it is a solution to 1. So it is actually an Einstein space, negatively curved Einstein space, so it obeys this curvature condition. And there is a metric that one can write in various coordinates, and I will write these metrics explicitly, so you can see explicit metrics. And moreover, it also solves 2. Actually, to show that it solves 2, it's much more involved. So I'm not asking you to check that, but it's possible to find explicitly the spinors epsilon in any given dimension. So to do this computation, as usual, you pick a dimension because you have to write explicit gamma matrices. So let's say you are in 4 dimensions. Then you write this equation here with some 4x4 matrices and so on. And then you can find explicitly in some coordinate system the spinorial parameters epsilon, and you will find actually several independent solutions, as many independent solutions as the number of independent entries of the spinor in that particular dimension. So in that sense, is a solution which is maximally supersymmetric, another notion that will recur later on. And not only is this maximally supersymmetric, it is also, in the technical sense of the word, a maximally symmetric space. So maximally symmetric space, I believe that the definition is that it solves this equation here. So the Riemann tensor obeys this equation here. It is just a combination with appropriate symmetry properties of the metric. So let me write this: G mu rho, G nu sigma, G mu sigma, and G nu rho. Symmetric. And indeed, if you take, this is the Riemann tensor, if you take just the trace to compute the Ricci tensor, you will find that this equation here is obeyed exactly with this factor. In fact, you can see that this is solved. So to put them into some kind of a little table, maximally symmetric spaces I can define them in Lorentzian signature as well as in Euclidean signature. And I can define them to have positive curvature or negative curvature. So in terms of the cosmological constant notation, I have the following. So I have anti-de Sitter if I am in Lorentzian with negative cosmological constant. Whereas I have, as I hinted already, I have the sphere as a very round space, and very round here technically means that it satisfies this condition with appropriate sign changes. And then you have two other cross cases. One is called de Sitter for obvious reasons, and this is the hyperbolic space in some notation. Okay, so these are the maximally symmetric space. So one way to think about anti-de Sitter is a sort of analog of the sphere. I'll make this analogy even sharper in a few seconds. So it's a very round piece, very round object, very symmetric, and in particular it means that it has a lot of Killing vectors. So the symmetry group is a maximal possible in the signature, given the constraint of the signature. I will write that next. So to make these considerations a little bit more explicit, we can introduce the following point of view. So we can view anti-de Sitter as an embedded space in some higher dimensional flat space of a funny signature. The signature will be something comma 2. So if we are in R2d-1, so that's one dimension higher than the dimension of anti-de Sitter that we're interested in, then we have various coordinates on this flat R2, d-1. Let's call it x0, x, d, and xi, where I goes between 1 and d-1. Okay, so these are d+1 coordinates. And I can write an embedding equation as follows. See this L that I wrote earlier reappears here. It's exactly the same L. And the claim is that the metric on anti-de Sitter is obtained from the metric just on flat space, just the flat space metric in this signature, once you impose this condition here. So in this sense, it's also very similar to the sphere, right? So if we are in Rn, in Euclidean space, and this was just all pluses, this would be a sphere of radius L. Instead, because of these funny sign changes, then we have the following. Zero square minus dx d square minus either plus sum dxi square. Okay, so these sums, sometimes I suppress all the indices, but let's write these ones. Goes between 1 and d-1. Okay, so that's a flat space metric. You plug this in and you get a metric on the induced space, which is exactly the metric by definition of anti-de Sitter space. And you can check that it satisfies all these conditions here that we want. So from this presentation here, it is clear, it should be clear, that the isometry group is actually O or SO 2, d-1. Exactly as O d+1 is the isometry of the sphere in d dimension. So this constant L, which in the case of the sphere would be the radius of the sphere, is also referred to as radius, and sometimes, often the quote marks are suppressed, of ADS. The quote marks are there because, as we will see in just in a moment, and as I have already anticipated, the anti-de Sitter space is a non-compact space, so it hasn't a finite radius. But there is a constant, a dimensionful constant of the dimension of length, which characterizes the space, and it appears here exactly as if it was a radius, if we were in a different signature. And to appreciate more explicitly these considerations, we can solve this embedding equation here in terms of some other coordinates, which are then unconstrained, exactly as we do when we introduce polar coordinates, just in, say, in a plane or in a higher dimensional sphere. And actually, different ways of solving this equation will lead to different canonical coordinate systems, which are useful for different applications. So I will mention a few of these coordinates. Each of them has their own virtues, and they highlight different aspects. There will be one coordinate which will be used mainly in the rest of the lectures, but let me mention also some other ones. So one is called global coordinates, and in these coordinates, this is called global anti-de Sitter. And the way to solve the embedding equation is to introduce d coordinates as follows. So this is very similar to the polar coordinates. So all of them proportional to L, and then one of the temporal direction gets multiplied by cosh over coordinate rho, cos tau. This has a cosine hyperbolic of coordinate rho, sine of tau, and this has sine hyperbolic of rho, and then some omega I, where the omega i's are exactly the polar coordinates on a sphere, actually a sphere of radius 1. So these are coordinates on S d minus 2. Okay, so here you can introduce theta, phi, psi. You're used to this. And the novelty, for most of you perhaps, is that you can solve similarly also for the non-compact directions with a negative signature by simply defining this coordinate rho, which appears in the cosine and sine hyperbolic. So rho is, by construction here, is a non-compact coordinate, whereas tau is a compact coordinate. So tau, because it appears inside the sine and cosine, has periodicity 2 pi, whereas rho, the natural range of rho, is between 0 and infinity. So it is on the half line. So I leave to you to actually plug this in, or do it in Mathematica, whatever you preferred method. It is completely trivial to find out the metric in the rho and omega coordinates, and this is given by ds square anti-de Sitter d has this overall factor of L square minus cosh square rho d tau square plus u rho square plus sine square rho d omega square d minus 2. Okay, so this is the round metric on a sphere in 2 dimensions. In d minus 2 dimensions. That's 2 for d equal 4. And the other comment is that you see the sine and cosine have completely disappeared when you have solved that. And there is one clearly temporal direction, which is tau, which appears with a minus sign. But tau here ranged between 0 and 2 pi. So the technical thing that we do is that we take the so-called universal cover, which means that we take tau in again in R, well, in R. So it can be any real number. Right. So this is now this has now not any more pathologies that would be otherwise closed time-like curves if tau was a periodic coordinates, and we don't want that. So after having done this universal cover business, this is what is normally referred as a global anti-de Sitter, or anti-de Sitter in global coordinates. Right? So this really highlights the global structure of the space, as opposed to other coordinates where the global structure is more obscure, such as coordinates which I will introduce now, which are in any case useful for many applications and many computations. There are two comments which I wanted to make. I will not write anything to speed up a little bit. So you can check that when rho goes to 0, the metric is smooth and completely regular. And in fact, the topology is that of R times R B minus 1 near to rho equal to 0. And you can also check, simply by looking at the asymptotic behavior of the sine and cosine as e to the 2 rho, that as rho goes to infinity, there is an asymptotic, what's called conformal boundary. So basically, you get a metric, which is a metric on, as rho goes to infinity, you get a metric which is a metric on the real line times a sphere. But this metric is multiplied by a growing factor. It's called warp factor, which grows exponentially. And this is what's called, in some more technical language, a conformal boundary or conformal structure. And that plays an important role in the context of the ADS-CFT correspondence. Let's move on to another common coordinate system, which is called Poincare coordinates. And for reasons which I will explain shortly, that is also called Poincare patch. If there are any questions, feel free to ask. And any kind of questions, really. All right, so this is slightly longer to write, but you can solve. The best way is to go back to the embedding coordinates, xi, x0, xd, and introduce the following. So here we make a further distinction between xi with I going between 1 and d minus 2, and the d minus 1 coordinates. Okay. So this is given by 1 over 2r, 1 plus r squared, L squared, oh, sorry, R squared, yes, L squared, plus x vector squared, minus t squared, 2 parentheses. This is simpler. This is L, R, t. This is L, R, xi. And this is longer, 1 over 2r, 1 minus r squared L squared minus x squared plus t squared. I think the change of coordinates between this tr and xi and the global one is quite complicated, but if you go through this, it's relatively simple. So again, it's a simple exercise, and let me write here in the corner what you find at the end of this exercise. You find a metric which is again one factor of L squared overall, and then you have dr squared over r squared plus r squared minus dt squared plus dx with the vector on top squared. Okay, and these we can also write commonly in this notation as just a flat metric on a Minkowski space. So in these coordinates, the coordinate which is non-compact is r. So as r goes to infinity, you find a conformal boundary, which now again has a divergent factor, growing warp factor, but the metric that you find explicitly here on this conformal boundary is the flat metric on the Minkowski space, as opposed to the metric on a real line times a sphere there. So this is not much different at infinity, but as the natural range of the coordinate r goes to 0, you don't quite reach the same as this rho going to 0, but you kind of, the space terminates sooner. So r going to 0 is a horizon. So it's a horizon, for example, because the Killing vector d by dt in these coordinates has norm that goes to 0, as you can see when r goes to 0. But it doesn't mean that there is a singularity. It's a perfectly regular metric. It's a perfectly regular horizon. And by standard exercise, you can continue the space past the horizon. And in fact, the best way to do that is to go back to global coordinates, and we'll find that behind this horizon there is still some space. So this is normally referred to as Poincaré patch. Okay, so this covers only a wedge of the hyperboloid that is the full global anti-de Sitter space. Other common coordinates, and then I have to stop because I could go on at infinity for infinite time by giving changes of coordinates. But common coordinates which are used in the literature are this one. That's very nice and simple to remember, and I will use this later on. Right? L squared multiplies everything. And that's simply obtained by doing r equal 1 over z. Or, so that's another coordinate system. Yet another one is r equal to e to the y, just to give a different name, in which the metric looks like L squared dy squared plus e to the 2y dx mu. So for example, let me point out that in these coordinates here, the boundary, so infinity, is reached as z goes to 0. Right? So you should not do the naive mistake of thinking that infinity is something has to go to infinity. Well, it's 1 over z that goes to infinity. All right. As I said, by making a joke, I could go on and give more and more different coordinate systems. In fact, in the literature, you can find more examples. Sometimes the metric that one discovers really looks very weird, but then you have to work very hard to show that it is just some simple metric in some weird coordinate systems. So there is no end to this exercise, but these are the most common and the most useful. Okay, so I can now move on and continue my journey into supergravity. Now I've shown that anti-de Sitter arises as the supersymmetric solution of the simplest supergravity, actually in any dimension, that's true, and in particular in d equals 4, which is our main example. And now I want to start generalizing a bit the supergravity that I start with in order to then find more general solutions with different, with additional fields and so on. Is there any question at this point, since we kind of finished the chapter 0? Okay. So the next topic which I want to discuss is that of minimal gauged, right? So there is this word gauged, which you have heard already about, supergravity. And to be definite, I will be here definitely in d equals 4, because from now on the details really matter. Well, there are out there experts on gauge supergravities, and they can write down Lagrangians with hundreds of scalars and hundreds of vectors and so on. I'm definitely not an expert on that, but I can tell you the main information and the main physics which is inside the idea of gauge supergravity, and how that ties in with this discussion of anti-de Sitter, and then later on how it ties in with the ADS-CFT. So one possible perspective is the one that I alluded to before, namely, what do I need to do in order to make sure that my action is really supersymmetric beyond linear level in the fermions? But I also told you that actually you can do that in d equals 4 without worrying too much. So I'm going to take this example not for that reason, but for the reason that is particularly simple, and it's also traditionally the dimension in which supergravities were developed historically. So although it's possible to write a full nonlinear supersymmetric action in d equals 4, I would like to extend that construction that still exists by adding more fields. So I'm not obliged, but I want to add more fields and see what do I need to do. And the word minimal here then means that after I add, say, well, let me explain. After I add an additional field, which is the Maxwell field, then what is the minimal completion? So let me write the fields. So we have the graviton, and we have a gravitino, right? So this is the very minimal theory to which I can add a cosmological constant. But I would like to also add a Maxwell field, so a field which is really a abelian vector field, gauge field. And to do that, then it turns out that I have to introduce also another gravitino. So in a conventions in which these are Majorana spinors, there are two Majorana, and then I can group them together in a Dirac spinor, which I will call psi mu. Okay, and I will from now on essentially forget about these different Majorana components of the Dirac gravitino. And what is about the gauging? Well, this is a gauge field, but what is it gauging in this case? It is gauging the symmetry which is given by acting on the gravitino, which is a SO2 that rotates these two gravitini, which is the same as, as U1. So this symmetry here, I'm not sure if you have seen this already, but in the context of global supersymmetry is called R symmetry. So it's a symmetry that acts on the supercharges. And in this case, it also acts on the gravitini. So in a representation in which we take this to be a complex field, then we have this U1, and this is exactly what this is gauging, right? But now, after having introduced the field content, then we have to write how to arrange this in the action and in the supersymmetry variation. And the gauge principle will, again, tell us how to do that. So the way in which this modification is introduced is following somehow the same logic that you follow when you start with the Dirac action and you want to couple to the photon. So you have to gauge the global U1 to obtain a local U1 symmetry, which is the gauge symmetry. So it is exactly the same logic. So actually I can start from the covariant derivative and then write the action later on. So now we have the covariant derivative, which by slightly changing notation, I will write in this way. Right, so this is now the ordinary covariant derivative of GR, and it is gauged with this factor of I over L A mu. So this is really d mu plus 1/4 A mu. And in terms of this modified covariant derivative, this gauged covariant derivative, I can write down my action. Now d is equal to 4. I have my square root of the determinant, and I have various terms. So I have R, and then I have this psi mu, gamma mu nu rho, d nu psi rho, plus 2 over L, psi mu, gamma mu nu psi nu, plus 6 over L square. You can check that I have been consistent with this 6 as coming from d equal to 4. And so these are basically the old terms, apart from this covariant derivative, which is now modified. But then there are extra terms, which you well, they should not surprise you. So there is a kinetic term for the gauge field, for the photon. And then there is also a coupling of this field strength with the gravitini itself. Gamma nu, slightly cumbersome in the structure, but never mind. Okay, plus cubic terms. So these beasts I'm ignoring as essentially many references. So the claim is that now this is supersymmetric if I do some supersymmetry variations which are modified with respect to the previous supersymmetry variations. So now I have to modify the variation of the field bind and the variation of the gravitino, and then I have to supplement it with the variation of the Maxwell field. So let me write that. We have d mu A is equal to, now your concern kicks in. I have to take here the real part of this bilinear, gamma A psi mu, and delta psi mu is equal to, let me write this first of all to make my life easier for now, and then the variation of the photon, which is actually again given by bilinear, simply the imaginary part of epsilon bar psi mu. So the structure is kind of you see, almost imposed on us by the index structure, or what we can do. And even this object here is the expected one. So the hat now is I'm building this up, so it's the original covariant derivative. Okay, d mu plus the bit that we introduced to introduce the cosmological constant, gamma mu, plus a new bit, which is this I over 4 f nu rho. This is slightly weird because it involves the field strength. Gamma mu. Okay, so at the price of defining a yet more complicated operator, you can re-express the gravitino variation in this way, and then if I set this to 0, this will define my Killing-Spinor equation, and the epsilon that satisfies this equation here will be a Killing-Spinor. Now, a configuration that solves this equation here has to have a particular g mu nu, a particular a mu, and a particular epsilon. And of course, I'm setting the gravitino, both real components, to 0. Let me also remark that this Lagrangian here can also be embedded in a very precise way in higher dimensions. So in particular, there are known formula, there are known expressions for relating this Lagrangian to 11-dimensional supergravity, something which I will turn to perhaps in the well, maybe not to, maybe on Thursday. But the next topic after this will be 11-dimensional supergravity. So the interest in studying this supergravity is not purely because it's a simple model, it's a toy model, but it has also a deep connection to string theory through the embedding of this into 11-dimensional supergravity, and therefore the connection to string theory becomes very concrete. So another name for this action is Einstein-Maxwell, for obvious reason. Einstein-Maxwell. And sometimes one calls Einstein-Maxwell also if you don't have the cosmological constant, so you have to say Einstein-Maxwell plus cosmological constant. That is really what this action is. It is the supersymmetric version of that, right? So it's the supersymmetrization of the Einstein-Maxwell action plus the cosmological constant. But obviously, this action here, the bosonic part, has been studied a lot already since the time of Einstein. So I would like to use the last part of the time today to discuss a bit about the equations of motion and the supersymmetry equations of this action, and give some examples which are also relevant for ADS-CFT correspondence. So let's write the equations of motion. So since it's an Einstein-Maxwell theory, there will be Einstein equations and Maxwell equations. Okay. So the Maxwell equation, I will switch to better notation. Take this form. No complaint. Whereas the Einstein equation take the usual form, where the energy momentum tensor of the Maxwell field, let me write it explicitly since it's quite short, okay, so F square means F mu nu contracted with F mu nu, and this you know what it is. So if I'm interested in solutions to this system, and in particular to supersymmetric solutions, I could consider, actually I ask you, what is a solution, supersymmetric solution to this theory different from Minkowski space, which we have already discussed? Sorry? That's too advanced, and you need to say more about what you mean. But something which I have already discussed. Simpler. Which one? ADS in how many dimensions? Yes. So sorry, this was a stupid question, but ADS4. Yes, right. So if you set f to 0, that's trivially solved. That's trivially solved, and then you get this is the equation for ADS, written already in the form where I have taken the trace and substituted. So I've written it in this way. So there is no explicit Ricci scalar in the formula in the Einstein equation. But of course, we could be interested in other solutions. So apart from ADS4, what are there other supersymmetric, and SUSY is a shorthand notation for supersymmetric solutions of this theory. So in particular with f mu nu different from 0. And actually they exist. I will show some example, and they are exactly of the types that in the audience that were mentioned. For example, there are particular BPS black holes that do that. So for the ADS-CFT correspondence, what we are interested in are solutions which are, okay, fine, supersymmetric, but even more fundamentally, if they're not anti-de Sitter itself, they should have some features of the anti-de Sitter. So the feature is that they should approach asymptotically anti-de Sitter. So we are interested in solutions, at least for the ADS-CFT correspondence applications, that are asymptotically, abbreviated A, anti-de Sitter. There is even a more technical nomenclature where they can be only locally asymptotically anti-de Sitter, which is slightly weaker condition. But at this level, for us, we just want to have something which near to the boundary, it looks more and more as anti-de Sitter, and then inside the boundary, inside the bulk, will be some modification. And of course, in general, for applications, we are also interested in solutions which are not singular. So that's something that we have always to keep in mind. Now, let me take this opportunity to mention another slightly tangential piece of information and body of work, which is not directly related to the ADS-CFT correspondence, but it is very much related if you're interested in the supersymmetric case. And that is that of the topic of how to address supersymmetric solutions. So there was at least one question from my former student, which was here. So at least now you should not sleep and listen to this discussion. But it may be of interest to other people too. So there are systematic ways to address whether the solution to this equation here. And in order to illustrate that, let's consider an example. So we construct this bilinear in the Killing spinor, which you can check from the fundamental properties of gamma matrices and spinors, that it's a vector. So it transforms as a vector under Lorentz transformations. So this is a vector, and it is also real, although the objects here are all complex, but in the end it's a real vector. But now this equation here implies some interesting properties of these vectors. Mainly, it implies that it is a Killing vector, so it obeys this equation here. So the Lie derivative along this vector of the metric is 0. And the reason why I indicate it in this way is that also the Lie derivative along this vector of the field strength is 0. So this is really a symmetry. This generates a symmetry, namely a U1 isometry of the metric, which is also a symmetry that preserves the field strength. So by a short computation, which I am suppressing here, but it's not too difficult to take, and if you're interested, you can attempt that and ask me if you have doubts. You can take that definition and then just from this equation, you can check that these follow. And this opened the way to the systematic study of supersymmetric solutions. So the idea is that you can find out as many as possible constraints that the supersymmetry equation imply on your geometry, namely on your bosonic fields. So from these equations, the spinor has dropped out completely. And these are equations which have a very clear geometric meaning. For example, this fact allows you to introduce canonical coordinates which are adapted to the scaling vector, where the metric takes a particular form, and so on and so on. So if you take this idea more seriously and you continue and you compute even more equations, then at some point, after a lot of work, and these computations can become quite tedious, but they are quite systematic and have been systematized over the years, you can find the necessary conditions that your geometry have to obey in order for a supersymmetric solution to exist. So this is a very general construction. It goes under the name of G-structure techniques or spinorial geometry or some variation of that. Generalized geometry is also another thing which is related. So in this way, you can pick your favorite supergravity theory and then study the supersymmetry equations. And if you have enough time and patience, you can classify all the solutions. So this has been done for many, many cases in the literature, and it has been done in particular quite a long time ago, around 10, 15 years ago, for this theory here. Right, so the equations can be written down. They are not so manageable to discuss them in the context of these lectures, but I can give you some simple examples. Of supersymmetric solutions of this theory here. So one quite general class is called self-dual solutions. And they are characterized by the following fact that in some conventions, the two form, the field strength of the photon is self-dual or anti-self-dual. It depends on the convention that you adopt. This is the Hodge star, so it's a condition that you can write down only in even dimension, and in particular it's quite famous in 4 dimensions. It's kind of a cute exercise, which again you can do in the back of the envelope, to show that this condition here implies that the energy momentum tensor vanishes, and therefore this has to be an Einstein space exactly as ADS. In fact, ADS can solve this equation where with its F is non-zero, but it is anti-self-dual. Moreover, the Maxwell equation from this, it's also automatic. That's trivially implied by the fact that dF is equal to 0. If you plug this condition inside the Killing-Spinor equation, which is this with the appropriate d hat, then you also find another interesting geometric conditions. You find that the Weil tensor, which I'm not going to define today, you can ask me later if you want. So this tensor, which is some combination of the Riemann tensor, the Ricci tensor, and the metric itself, obeys this condition here, right? So it is also self-dual in two indices, which is the reason why these solutions are referred to as self-dual solutions. And for more geometrically minded people, this condition here means that is also called that the geometry in Euclidean signature is called quaternionic Kähler geometry. So there is a very rich structure, again, that relates to geometry, which emerges from this quite simple supergravity. And it is not unrelated to ADS-CFT. For example, you can already appreciate that I said you can consider anti-de Sitter space, which is clearly relevant for ADS-CFT, plus a non-trivial anti-self-dual field, which is sometimes called an instanton. And in fact, this has a nice application in some work of mine in some years ago. We studied that. So there is a, if you continue along this path, there is a quite nice ADS-CFT, ADS4 CFT3 story that unfolds from here. Another set of solutions, which is perhaps a little bit more hands-on and more physical, or at least more easily appreciated that they are physical than this class of self-dual solutions, which are also physical, which are some kind of particular black hole solutions. So, for reasons which I have not time to discuss now, black hole in anti-de Sitter have become quite popular and well studied in recent years. Recent years means in the past 2-3 years. And it's quite an intensive topic for work. So in 4 dimensions, I can consider so-called anti-de Sitter black holes. Which means that our space-time is a space-time which asymptotically approaches anti-de Sitter 4. So you can imagine this as pictorially as some anti-de Sitter, where in the middle, in the center, you drop a black hole in the middle. Okay, so instead of the previous anti-de Sitter, you have a black hole, or conversely, you can imagine a black hole and then surround this with anti-de Sitter at infinity, putting in kind of in a box, we used to say. So to make this completely concrete, I can write down simple examples. So let me write one very simple example, which which relates to some physics that you probably have seen before. So I can write very humble line element in terms of a single non-trivial function of one variable r. And the slight novelty is that locally this metric here has to be a constant curvature metric with negative curvature. So it is a metric on the hyperbolic space in 2 dimension, which you can make compact by means of quotienting by some discrete group. So if you quotient that, you get some compact surface. But in some sense, this plays the role. So this plays the role of a 2-sphere, right? So it's as anti-de Sitter is the negative curvature version of a sphere. This is in my table with 4 entries. Hyperbolic space was one in Euclidean signature with negative curvature. Let's write the function. Function f of r takes this interesting form, which is interesting because it's a perfect square. Okay, and the fact that it's a perfect square, for those of you who are already playing around with these metrics, it's a strong hint that there is some special property of this metric. And the special property is actually that this metric here, it preserves supersymmetry. Moreover, if you do your standard exercise about black holes, you will find out that there is a horizon when this function vanishes and r takes some particular value. But it is a slightly non-standard type of horizon, in which this function, which normally has a single zero, has a double zero where it vanishes. So what I mean by that is that you can compare with your preferred black hole, which is Reissner-Nostrum. So I'm comparing how's it spelled? Nordstrom. Well, okay, sorry about that. So the Reissner-Nostrum black hole is also a black hole in 4 dimensions, typically studied in 4 dimensions. And it has a spherical symmetry, so it has an S2 factor and only a function of radial coordinates r. And what is the function? So for Reissner-Nostrum, it is a function of r, which is not a double root, but there is a simple root. So that's the Reissner-Nostrum. Sorry, this is supposed to be an n function. So you can compare. So it is exactly the same magic, with here a 2-sphere and this function here replaced by that. And what are the physical differences? First of all, in general, the Reissner-Nostrum magic does not preserve any supersymmetry. And moreover, for r going to infinity, we see that the f that I wrote goes like r squared over l squared, whereas the f Reissner-Nostrum goes like 1. So this is well known to be an asymptotically flat black hole, whereas this is an asymptotically locally, actually, ADS4. Locally, I'll put in quote marks because I don't want to define. But you can see what this means. Basically, you can find out what this means, because the metric as r goes to infinity approaches this form. So that's a typical calculation that you do if you have some metric which you would like to find out about its asymptotic. You just expand it near to where the asymptotic is. So this is r goes to infinity in these coordinates. And then you reconstruct at leading order. So this wiggle term means at leading order in r going to infinity. Okay, and if you compare with the metric in global ADS, which I wrote about an hour ago, you will find that if this was an S2, that would be ADS4 in global coordinates. The fact that in fact this is not S2, it means that this is not just asymptotically ADS4, but it is asymptotically locally ADS4. So the metric at the boundary is not conformally flat, which is what this locally means. Also, note another fact that if you set, so there are 2 parameters here. So here there was only 1 parameter, which is the same as the cosmological constant, and essentially it's the same parameter that enters here. But if you compare with the parameters which enter in the Reissner-Nostrum metric, you will find out about the physical significance of these parameters. And in particular, Q is related to the charge of the black hole, and m is the mass of the black hole. So in this particular condition that you have Q square equal to 4 pi g Newton equal to m square, then this is called Bps condition. And in this case, the Einstein-Nordström black hole also becomes supersymmetric, but it is a supersymmetric solution of a different theory from the one that we started with, right? Because there is no cosmological constant. So it is just the same supergravity as before, but where the cosmological constant has been put to 0. So actually, to recover that from our, you have to do a little bit of a gymnastic. It's not very convenient because you have to send L to infinity and so on, but you have to go back and just set the cosmological constant to 0, and that would be your canonical Einstein-Maxwell theory. Okay. Right, so the comment here, just to finish, is that this condition of a charge equal to mass, quite generally, it's a strong indication, is almost taken as a synonym of the fact that some supersymmetry is preserved. This goes back to the original work of these people, Bogomolny et al. And if you compare with the solution here, which is already supersymmetric by itself, there is no parameter to tune, that the fact that you can write this as a perfect square is already suggestive that this is relating the mass and the charge exactly as it's happening for the Einstein-Nordström black hole. So I think I've said everything I wanted to say today. So there is no need to continue for long, because next thing I would like to talk about supergravity in 11 dimensions. But if you have any questions about what we did today, please go on now. I can stay for a few more minutes, as you prefer. I'm done. Sì. Cioè,